adjust myself to that by kind of offering a choice about a very brief discussion. Well, first I'd like to just round off what I was saying, describing in my last lecture, by looking at the ways that one can prove that the required moments of the estimators or the t-test statistics are finite. What I've always found it useful to do myself is to make use of various inequalities for this purpose, and I might, every case that one discusses is a matter of working out some appropriate inequalities, and there are a wide range of inequalities to be used, some of them turning on the properties of positive definite matrices and their latent roots, some of them being straightforward Cauchy inequalities, and some of them just depending upon the properties of determinants or something of this sort. Let me very briefly illustrate this sort of thing by looking at the case that we've been looking at up to now, where we're estimating an equation and we're using a set of instrumental variables so that the estimator that we're interested in can be written in the same notation that I've been using before. And then so y is the constant coefficient equation, x are the other variables in the equation. X may include both endogenous and predetermined variables, and the z's are the set of instrumental variables. An idea which is often useful is to notice that such an estimator is obtained by using minimizing by minimizing the function u z z prime z minus 1 z prime u, where u is given with respect to a, and if we use u hat to mean the corresponding estimates of u, in other words defined in the usual way by putting hats on both a and u here, you can make use of the inequality that is less than or equal to the corresponding thing. I won't bother to put bars here, but at this point I'm switching to the idea that the u is actually the u which corresponds to the true value of a. So we have that inequality. Of course, it's convenient at this stage to denote this matrix that we have in the middle here by something else, and let's denote that by q. So we have u hat prime q u hat less than or equal to u prime q u. Now, what I want to do is now to look at the difference between a and a hat, or correspondingly to look at the difference between u hat and u. And so what I'm interested in is putting an inequality on u hat prime minus u prime q u hat minus u. Well, now if we expand that, of course, we can expand it in the form u hat prime q u hat minus 2 u prime q u hat plus u prime q u. Now, what we know is that u primed q u hat modulus is less than or equal to u hat primed q u hat u primed q u to the half. So it follows that minus this is certainly less than this. Okay, because, in other words...
That's missed a moment ago. That's u prime q u hat, is it?
Yes, modulus. And the point is that minus u prime q u hat is less than or equal to this, because it's either positive or negative, and if it's positive then it's equal to it, and if it's negative it's less than it.
The half applies to the whole bracket on the whole thing.
Yes, I'm sorry, yes, okay. I ought to put one further bracket around here. That's the Cauchy inequality, or Cauchy-Schwarz inequality it's sometimes called. So what we can do is to put that in here and then realize it tells us that this is less than or equal to, and at this stage it's going to be u hat primed q u hat prime to the half plus u primed q u prime to the half all squared. If you square that out, of course you get the first term corresponds to the first term here, the second term corresponds to the second term here, and the product here by this inequality is greater than the u prime q u hat. But now, of course, we can use the inequality that I first stated, that u hat prime q u hat is less than or equal to u prime q u, to say that that is less than or equal to 2 u primed q u to the half all squared, and that is less than or equal to 4 u prime q u. Sorry, that is equal to, sorry, no, less than or equal to, that's it. That last term is equal to, just squaring it up. Well, that's a little known form of the Cauchy-Schwarz inequality, but it's the one that one usually finds it possible to use. Well, I will only go one more stage in establishing this kind of inequality, because what I wanted to do really was to give you a kind of sample of the kind of arguments that is being used, and they're all based upon, if you like, matrix algebra type inequalities in effect. What we now have, you see, if we substitute in again, is that we have a hat minus a primed, a again being the true value, into x prime z, z prime z minus 1, z prime x, a hat minus a is less than or equal to u prime q u. Sorry, 4 times up. The factor 4 doesn't matter very much, of course. It's all one's interested in is proving boundedness. Well, now that's got us so far. Now, as I say, one often finds it useful then to introduce relationships involving the latent roots of the matrices we're dealing with. This is a matrix we have in here is non-negative definite, and of course positive semi-definite with probability 1. And so what we can do is to introduce lambda m for the minimum latent root of, well, let's define this as r which is x prime z prime z minus 1 z prime x. I'm just introducing my definition of r so as I don't have to carry on writing down that whole thing.
That was Q a moment ago. Oh no, sorry. Yes, okay.
Q is the actual z prime z minus 1 z prime. R is the estimate of the asymptotic error variance matrix inverted. Something that's always turning up in this instrumental variable field. And then what you have is that r minus lambda m I is non-negative definite. The minimum is supposed to be latent root. And so what that means is that a hat minus a primed r minus lambda m I into a hat minus a is greater than or equal to 0. So then at that stage you see that lambda m times a hat minus a prime a hat minus a is less than or equal to a hat minus a prime r a hat minus a is less than or equal to u prime q u. Now these manipulations look, rather arbitrary. Where is one going to get in the end of all this? At this stage you can start using inequalities on the latent roots and the traces and the determinants of the R matrix. But the point of the first manipulation, let's explain why it's worthwhile to use this Cauchy inequality in the first place. The reason for that is that if you approach directly the definition of the A hat, you find that what is going to cause the A hat to become large is if x prime z upon t it tends to be of too small rank, because then, just to state dimensions, this should be n by m, where n is the number of variables, coefficients being estimated, in other words, the number of variables in the equation apart from y, and m is the number of instrumental variables in the system. So what is going to cause the A hat to become large is if the rank of this is, approximately equal, less than, or equal to n. In other words, if it's going to tend to be of less than full rank, because then you can see that what will happen is that the R matrix will become singular, and therefore that when you invert the R matrix to get the solution of for A hat being defined as R times x prime z, z prime z inverse into z prime y, then A hat will become large when R becomes nearly singular. So this is, if you like, where the polar set, the set of values of x and y, which makes the A hat large, it's in the neighborhood of x prime z upon t, which are of less than full rank. Now, on the other hand, you find that because there's an x prime z, z prime z minus 1 in the top here, as this r becomes singular, and therefore r minus 1 becomes very large, part of the effect of that is cancelled out by the x prime z, if you like, tending to be of less than full rank in the same way that the x prime z that's occurring below is of less than full rank. And so, though it looks at first sight as though the moments of A hat, you know, if you ignored this factor and looked at simply the moments of R minus 1, you'd find that you've got a quite different answer to what you get when you consider A hat itself, this product. And the Cauchy inequality that I've used gets round that, in effect, by you know, rather a neat way of giving you the right result, and at the same time, what you have to realize is that it's relatively easy to prove that if this sum of squares has moments of order k, then A hat minus A itself will have moments of order 2k. So that essentially, if we can discuss the moments of this product itself, it's the same kind of simple inequality that's required to prove this result I've just stated, that if the kth order moments of this, or if you like the half rth order moments of this exist, then the rth order moments of A hat minus A exist. So it's enough for us to look at the moments of this. Well, I don't know whether I want to go on to illustrate the next stage, because if I leave you in midstream here, I've given you a kind of sample of the kind of inequalities that are being used in this field by continuing to work your way through these kind of inequalities, always making use of the idea that if one positive number here is less than or equal to another positive number here, then the moments of the right-hand side existing is enough to ensure that the moments of the left-hand side also exist. And it's that essential idea that's being used throughout. Well, that gives you perhaps some idea of the kind of arguments that can be used to show that the moments are finite. And that always seems to me then that the simplest useful approximations are given by the Nagar approximations, and that to try and work out the exact moments for more complicated estimators is not a very fruitful way of proceeding. So that's perhaps all that I want to say now about the Nagar moments. And now, in the final hour of these lectures, let me turn to some more practical considerations about the computer computation of the Edgeworth approximation. About 4 or 5 years ago, Yuxei and I received a research grant to develop computer programs for the computation of the Edgeworth approximations, and we wanted to set it up so that we could first of all, work out the cumulants of the second moments of any stochastic difference equation system. We didn't attempt to cover the case where the errors were moving average, and we defined the system that we were going to be considering in the form the xt being a set of m times 1 exogenous variables, the yt being an n times 1 vector of endogenous variables. So we have an rth order lag on the endogenous variables. Of course, one can include any number of lags on a set of exogenous variables simply by defining the xt to include both the current and the lag values of the exogenous variables. But the xt were just non-stochastic and could be specified as any set of time series. Now, we're assuming that the UT are white noise and are serially uncorrelated. Of course, one can regard the setting up of the cumulant distribution function simply in terms of saying that, okay, what you have here is a set of normally distributed variables yt with given means and given variance matrix. So the thing that one has to do is to set up the means and the covariance matrices for the normal distribution of the whole set of yt. What we did, in fact, was to consider t equals 1 up to t, and that involved, and why did I say yt plus s? I meant yt minus s. That involved also looking at the initial lag values for yt, so that had to go from t equals 1 minus r up to t. We had to take in the initial lagged values outside the sample period, if you like. We assume that the estimators are going to be based upon this sample from t equals 1 to t, and therefore that we would also be observing the lagged yt's outside that sample period. What we then would want to do is to set up the cumulant generating function for the moments, the second moments generated by this, and we were going to be looking at various types of things. In fact, what we did was to, because various possibilities arise, you see, of estimating the yt minus s I wanted to deal with the case where you had a possibility of factorizing out an autoregressive polynomial here, and perhaps then estimating by OLS on some sample out of here, and then estimating, for example, a Durbin-Watson ratio or some test for autoregression using data which would involve taking lagged values of the U's generated by the original OLS estimates. And so instead of looking at cases where all lags run over the whole sample, I actually looked at a rather more complicated idea that we would look at lags of this kind, second moments of this kind. You see that we have, in effect, t minus k observations here, lagged b time periods, and that we're then taking such a sample to estimate the lag of order A, or the second moment which lags the y's by a time periods. We considered all possible moments of this kind for finite values of A, K and B up to some order. Now, though the program allows you to compute that, usually you won't want to compute all of these, you'll only want to compute some simple subset out of all these possible moments, and you'll want to consider functions which are depend only upon some simple subset out of all these possible moments. In the same way, we looked at all possible moments involving an x and a y, and we considered exactly the same kind of definition. T minus k minus b, t minus 1 minus b, x a, t plus a, y t over t minus k. Sorry, I'm putting primes on these because, of course, this in general will be a square matrix, and this in general will be a rectangular matrix. Now, the essential idea is that we define our y to be made up of y primed 1 minus r up to y prime t. So our y matrix includes all those variables. We can also define vec y, and perhaps rather idiosyncratically, I'm just going to define that as y 1 minus r up to y t, where we simply write the whole matrix down as one long vector. And then what we want to do is to think of the each of these matrices as being a quadratic form in vec y. Now, in order to do that, I'd have to think about taking the trace of this matrix with some appropriate theta, what have we got here, theta s, where s is different for each separate, yes, I'd better explain that what we're interested in, if we think of all the elements of these matrices and these matrices as making up one long vector p, so we take all the elements in some order, we're going to multiply by p. Now let's differentiate between what I might call a pyy, which is the elements of the first type of matrices arranged as a vector, and pxy, which are the other lot. Then what I'm going to do is then to introduce a corresponding vector theta of parameters and a corresponding vector phi of parameters, each of the same dimension as pyy and pxy respectively. And then, of course, what I can do is to define my characteristic function here to be expectation of x of theta primed pyy plus phi primed pxy Now I say that's the characteristic function. It would be the characteristic function if I'd put in the I, the imaginary number, multiplying it. Since I find it convenient to work with real theta, real phi, this is really the moment generating function. Well now, how is this related to my introduction of a trace theta s here? Well, if you think of the effect, let me write this as a capital theta. If you think of the effect of introducing a square n by n matrix theta s, multiplying my yt plus a yt prime t minus k, you'll see that the elements of theta s, if you make theta s a general square matrix, the elements of theta s will correspond to the elements of my theta matrix here, and every element of this square matrix corresponds to one element of my pyy, and so you can think of yourself as getting the appropriate theta prime pyy by taking some summation over all moments that you're interested in of this kind. So for every s there's a corresponding k, b and a, and then you're summing up over all values of s that you're interested in. That sum will precisely correspond to the theta prime pyy that you have here. In the same way, if you take a matrix, shall we say phi, again let's use S to mean the set of second moments of this kind that we're interested in, then again you can take the summation over all such matrices of this kind that you're interested in, and of course you've got your trace to make them into a scalar. So this kind of formula is what we want to take the e to the x of in order to get the cumulant generating function for this set of moments. Actually, I should say the moment generating function. Of course, then to get the cumulant generating function, you'll have to take the logarithm of this moment generating function. Well, now, how do we proceed from here? Well, the next thing is to notice that, as I remarked before, if you look at each of these expressions, first of all the sigma trace, this thing, what you see is that it consists of a large quadratic form in vec y. And the quadratic form in vec y has coefficients which are linear in the elements of theta s. If you like to think of any particular element of theta s, it's picking up a corresponding element of this matrix, and the matrix, each element of this matrix, is a quadratic form in the elements of y. So you can think of yourself as having a large quadratic form, and you can think of this whole expression here. So I'm taking the first expression, this trace of sigma, and it's the y theta s. I won't bother to put in all those suffixes. And you can think of that as being written in the form vec y, and I know there's a bit of, that should have been a capital theta s. I know there's a little element of using the same symbol, but at that stage I'll simply use capital theta to mean the coefficients of the quadratic form in vec y. Each element of theta is linear in the elements theta s in a way which I won't bother to spell out, but you can see that there's a simple linearity connecting any element of capital theta without a suffix with the corresponding elements of capital theta s. Now, in the same way, we find that if we vec x the same way that we vect y, that we can write that sigma or trace sigma s, and now it's going to be y. Yes, there are two sigmas. I haven't put enough sigmas in here. There's a sigma over s and there's a sigma over the coefficients, all possible coefficients in the yy. So there's a summation defining the moment here. In the same way here we have a moment that depends upon y and upon x, and in fact it's usually got the x first, so let me write it sigma s, then sigma over the t, and then y, x, y, with x and y having various suffixes, and as usual divided by t minus k, and then that's being multiplied by capital phi s. Well, that is obviously bilinear in vec x and vec y, and so I simply write it in the form vec x prime capital phi without a suffix vec y. And again, the elements of the phi matrix are linear in the elements of the phi s matrices, simply various linear combinations of them. And finally, to write this more simply, let's simply write it in the form of psi prime vec y, where psi is equal to phi prime times vec x. So now what our moment generating function consists of is the expectation of the exponential of vec y prime phi vec y plus psi prime vec x. And now what we do is to assume vec y is distributed normally with mean m and variance matrix omega y. Now, it's not too difficult to plug that into the distribution function. In other words, we're going to have determinant omega y to the minus a half, and also a constant 1 upon 2 pi to the half n into t plus r on the outside, and on the inside we're going to have exponential minus a half vec y minus m omega y minus 1 vec y minus m. And then, of course, what we're doing is to take exponential. We're taking this expectation here, and of course we're going to have this term repeated. I won't repeat it. And then we're going to integrate over d vec y. And this is all very standard. Theory, as for example applied in working out what the distribution function, or rather the moment generating function, is for a chi-squared. The thing is that exactly on all fours. What you find is that the product that you have to integrate involves the exponential of a different quadratic form, in which you have omega y minus 1 combined with phi. Why did I put phi? It should of course be capital theta. And you have, of course, yes, I've got two great Lumieres there, vec y there, and you have, if you like, a different mean here, because the psi prime has the effect of shifting the mean of the normal distribution. But that when you've sorted it all out, you get something which corresponds to a different normal distribution, where the variance matrix and the mean depend upon theta and psi respectively. And if you finally work all that out, you find that the result is the following: half log determinant omega y. Yes, I'm sorry, what I'm going to write down is the log of this function. I think it's rather easier to see it. That, of course, is just so log of this equals log of this equals omega y minus 1 minus a half m primed omega y minus 1 m minus a half log determinant omega y minus 1 minus 2 capital theta plus a half m primed omega y minus 1 plus psi primed into, now the same thing here again, omega y minus 1 minus 2 theta, all inverted. Then the same product again, omega y minus 1 times m plus psi. Well, I've given you rather perhaps more theory than you need at this stage, but what you see is that you can actually express this in terms of theta and phi analytically, because the psi depends upon phi, and you can easily analytically differentiate it with respect to theta and phi any number of times, and so from that you can generate the cumulants that you require for the edge of the approximation problem. And the computer, in fact, has the corresponding formulae for these cumulants, and so will generate all possible cumulants up to the fourth order of any set of moments of the type that I've specified. In fact, in this first paper that I'm really quoting from, we did this by using numerical differentiation procedures, but we found that the rounding off errors when you got to looking for fourth order derivatives were rather serious, and so later on we implemented the subroutines which would actually compute the cumulants analytically, actually work out the program actually had the formulae for the up to the fourth order cumulants stored, so that it would compute them directly from the omega y, the m, and the formulae it contained itself for the elements of theta.
So effectively you have to do all the work anyway, is that right? You've got to provide the code for the analytical derivatives after the fourth order.
No, no. This the program is stores these, has got its own subroutines for computing these. All you have to specify is the actual model in the form that it starts, and then it will accumulate. It will compute up to the required order analytically. Now, on the other hand, the other things that we require is, as you remember, that you have some function of these things that I've specified, what I was now calling E of P YY and PXY, and what the program then needs is the derivatives of the E PYY, E PXY, and there we did find that it was most convenient to simply take the function and differentiate it numerically about the true values, mu YY equals expectation PYY and mu XY equals expectation PXY. So in order to implement that, what you have to do is to provide a subroutine that would actually compute the E in terms of these PXX, PYY. And of course, part of the problem with using our program is to actually get the variables stated in the correct order, so that it agrees with that used for defining the cumulants that you have down here. But I don't think that's a great difficulty. It is explained in the program description, the program write-up, how to do that. Then the main program, the actual program itself, will generate all the derivatives that it requires by differentiating numerically. So in effect, all you have to do is to provide a subroutine for working out the estimator or the test statistic as a function of the PXX, PYY. You can do this anyway using either, specific algebra for each E, or usually what one needs is to write down a matrix algebra program for computing some estimator in the usual way. You note, of course, that E is always a scalar. The program doesn't try to work out joint multivariate edgeworth approximations. it really only works out marginal edgeworth approximations for one estimator. And what it does is to store first of all, work out the values of the cumulants and store these in the machine memory. And then you can use the same cumulants to discuss a set of E's which, in other words, you can look at more than one estimator or more than one test statistic, more than one function E, because what it will be doing is to generate the E's as it goes along, the derivatives of the E's as it goes along, and then combine them with the cumulants that it's holding in memory so as to compute the Edgeworth coefficients immediately. It doesn't try to store both sets of things, because that would in fact usually take up quite a lot of memory space as soon as you got onto largish models. So the basic idea is to store just the cumulants and then to use the derivatives of the E's as they're generated to combine with the cumulants to give you the Edgeworth coefficients. It generates the Edgeworth coefficients in Edgeworth approximations in two possible ways. That is either the method which involves the Hermite polynomials, combining the Hermite polynomials together and then applying them to the first derivative of the normal cumulant density, normal cumulative distribution function, which of course is the normal density, and adding that on to the cumulative distribution function. That's what I called previously approximation A. Or alternatively, it generates the approximations in the approximation B form, where essentially what you're doing is to look at something of the form I of, shall we say, H of R, where H is a polynomial. So it will do either of these. It will generate the approximate distribution function in either A or B form, and it will then print it out for various values of R, and you can specify what set of R you wish it to actually compute the distribution, the Edgeworth approximate distribution for. So it's fairly automatic. All you have to do is to specify the basic model that is supposed to be generating the data. That is the model that I started with, and to also provide the subroutine for calculating one E or a set of E's, and then it will specify what values of the R that you require it to compute the two approximations for. Of course, the approximations are to the cumulative distribution function rather than to the density. Assume that this is the best comparison that one can make. Also, in connection with this, Say wrote a general simulation program which would simulate for this general model and could then be used to produce Monte Carlo estimates for the cumulative distribution functions, which could be compared with these Edgeworth approximations. Now, the paper that I'm making use of here is the working paper, Some Experience of Numerical Computation of Edgeworth Approximation. And in that paper, what we did was to look at the simplest case that we could think of, just to see how the program worked and to give some illustration of the use of it. And though our general program was designed for sets of equations, the simplest thing that we could think of to do was to look at a single equation. And so we were looking at the y equals a, y minus 1 plus xb plus u type of model, where the x are some set of exogenous variables, generated as usual by using a simple first-order autoregressive model to generate the x's once for all. And the A, of course, is the autoregressive, or if you like, a partial adjustment coefficient. And we tried this for various values of A, keeping the B and the X fixed, and for various values of U, of the variance of U. Looking at, in this case, simply at the ordinary least squares estimator, written in the form y minus 1 minus, etc. Of course, our basic idea was not particularly to generate new information here, but to give the program a kind of test run. At the same time, of course, it was quite interesting to see what the effect was of varying various parameters on the goodness of the Edgeworth approximations to A hat, or the distribution of A hat. The advantage of doing it with A hat itself is that in this case there is the Imhoff procedure which will give you exact distributions for A hat, so you can compare the Edgeworth approximation with the exact or the Imhoff analytic approximations to the exact finite sample distribution. We were pretty clear that the Imhoff program was giving us errors of only 10 to the minus 4, and so we could treat that as being exact. You then have the problem of summarizing the difference between the two distributions. It's not really possible to print out all the graphs of all the cases that we considered. And we were looking at two criteria. One of them was simply the maximum difference between the two distribution functions. If we have, shall we say, f of r for 1, the exact one, and f star of r for the Edgeworth approximation, this is simply a matter of looking at max r of the absolute difference. But also we were particularly interested in how well these performed on the tails. That is really where you'd expect the worst approximation. And so we also looked at we took a symmetric confidence probability output and all this is fairly full.
I should have asked them, well, you need to know the results first of all before
Yeah.
they're worth getting.
Well, yes. There is a problem, you see, that, well, perhaps I say this on tape.
For the spatial cases for which people have worked out exact distributions, how do the approximations compare?
Well, we worked out exact distributions for all these cases that we're looking
I was thinking of the cases with two endogenous variables and simultaneous equation estimators.
Ah.
Those sorts of problems.
Well, I was just explaining that the second criterion was for a tail criterion, and that we were comparing the different estimators. We normally found that we did in fact have that A2 and B2 had much the same performance, which was usually better than A1 and B1, and that these in their turn were better than the asymptotic. As to the normal distribution, that sometimes worked out quite well, but in some cases was rather bad, and so was a little unreliable. And so we, in the end, decided that this normal approximation with appropriate mean and variance was not a good alternative. On the other hand, in all cases, we did have in the cases where the asymptotic approximation was very bad, we would find cases where the Edgeworth approximations were not reliable. What we did in order to try and correct the problems with the Edgeworth approximation was that, as you remember, there's a tendency for the A type of approximation to go outside the range from 0 to 1. What we did when the thing went outside the range from 0 to 1 was simply to say that the approximation was then 0 or 1 respectively. In other words, always take the approximation and correct it so that it lay within the bound from 0 to 1. So in deciding what the maximum error was in the approximation, when the thing had gone outside these bounds, we simply pushed it back inside and then looked at the error in that corresponding approximation. That often gave a reasonable approximation throughout, as we can see by the scale of the possible errors. Let me look at a kind of just a line from our table just to see how it went. The worst cases were when A was large, and we were looking at some cases where A was 0.8. In other words, cases where the partial adjustment coefficient was near the unit circle. And correspondingly, the worst cases from the point of view of variance was clearly where sigma squared was set rather large, and so we had cases where sigma squared equals 2, sigma squared equals 5. The corresponding value of r squareds for 2 was about 9, for sigma squared equals 5 was about 0.75. That's about as far as we went in having, if you like, a fairly high variance for the error on the equation. The obvious two cases that we took for t was t equals 20, t equals 50. As you'd expect, t equals 20 was rather worse. Let's have a look at a case where t equals 20. The A is at its worst value, but the sigma squared is at its medium value. You get the following maximum differences. These are, first of all, the asymptotic distribution, the maximum error was 0.168. Sorry, yes, 28 to 0.2215. In other words, though this was supposed to be an asymptotic normal, the probability of being outside the range was more like 0.27 rather than 0.05. So this is a case where we've got a very bad asymptotic approximation, largely because it's a equals 0.8. Let's see how the other things fared. A1, that's the first correction term in the edge with approximation of the A type, is 0.1174, so somewhat better. B1 is 0.0659. In fact, our experience was that B1 was usually better than A1. Then the A2, B2 were not very much better. A2, B2 not very much better at 0.0638. In fact, B2 was worse, 0.0699. Normal approximation, 0.1981. Now, on the other hand, that is with t equals 20. If I take t equals 50, just to see, you know, whether it really pays to have a bit larger sample, what you then find is 0.1349. So, okay, the normal, the asymptotic distribution is got reduced its error by a factor of about a half. The A1 0.0255. The B1 0.080, not at all bad. The A2 0.160. The B2 0.0285. The normal 0.1662. So normal definitely not showing any improvement. B1 again showing up rather favourably. In fact, B1 often did turn out to be quite a good approximation, about as good as the A2 and the B2. Not always, but quite often. Well, that gives you some idea that if you've only got a t equals 20 size, perhaps it's not worthwhile looking at anything except B1, but that for t equals 50, then A2, B2 come within the range of useful approximations. But you see that it's not always the case that the second order approximation is really better than the first order approximation. You'd have to look at all these tables to see whether there's any kind of average tendency for the second order approximations to be better than the first order approximations. I would say that I happen by chance to have picked out two cases where there isn't very much improvement, and that in some cases, particularly the sigma squared equals 5 and a equals 0.8 cases, they're actually worse, the second order approximations than the first order approximations, because they tend to behave rather badly on the tail more often. But that always what you find is that the Edgeworth approximations are a bit better than the asymptotic approximations, even when the asymptotic approximations are particularly poor. They're always, perhaps I should have given you a good case to look at as well, but let me simply generalize that when the asymptotic approximation is not bad, though I must say among all these parameters that we looked at, the asymptotic approximation was always underestimating the probability of being outside these confidence intervals by quite a significant margin. Well, just for a final comparison, let's look at what you might think of as being the best case for the asymptotic approximation, which is t equals 50, the largest sample size, a equals 0.2, the smallest coefficient, autoregressive coefficient, sigma squared equals 0.2, the smallest variance, and for that case you find the corresponding table as above, 0.0361, so still the probability is more like 9% than 5% of being outside the 5% limit. The asymptotic, yes, the A1 is 0.0012, the B1 is 0.0002, the A2 is unfortunately worse than the A1, and the B2 is about the same, and the normal is doing rather well at 0.0038. Still, all of these are between 5% and 6% in terms of what the probability of being outside the range. All of them, therefore, give us a much better approximation than the asymptotic distribution itself, which is quite a way off. So what one sees, of course, is that the goodness of these approximations is very model dependent, and very often it will improve on things, and particularly it will give you a better approximation, and perhaps you might say an indication of the direction of the bias in the asymptotic distribution, even in the worst cases. However, I don't myself feel that these are very optimistic results from the point of view of using edge-with approximations, because even in these very simple models we are still getting pretty large errors from the edge-with approximations, and it does look as though we have to think further about methods of improving on the edge-with approximation, particularly for these dynamic models. What does stand out from all the work I've done is how important is the parameter that corresponds to the 0.2, 0.8 here. In other words, the dynamics of the model, how close the latent roots are to the unit circle.
How heavy is the computational burden involved in these? Because you have fairly large summations involved there.
Yes. Well, the time is not excessive. Whenever we ran these things, we found that, but of course, we weren't looking at the big models. As soon as you move from cases like this, where we have, say, only up to, say, 10 separate elements in the P vector, to larger models where you could easily get up to 100, or if you went to a really large model, you'd get into thousands very quickly. And of course the number of computations required here is of the order of the fourth power, since you're looking at fourth cumulants and looking at every possible cumulant. That goes up very quickly with the dimensions of the P vector. So I don't think that what we've done here really throws very much light on that. For what it's worth, however, I can say that really it took only a few seconds of CDC time to work out the edge-with approximations. It took longer really to work when we got on to simulating. It took longer, of course, to do the simulations that we were comparing with. You see, for any other case than these very simple cases, there isn't the Imhoff finite sample distribution approximation, and you have to make use of simulations. And in order to get good simulations, of course, theoretically you ought to do at least 1,000 simulations. Better still to do 10,000, or as Jim Durbin did in his Biometrical article, 10,000. But we were actually working with 1,000 simulations.
Why is that the first approximation is first order is better than the second order approximation in the experiment?
Well, it shouldn't be, that's all I can say, but it usually was, as I say, because we're taking the maximum, and the second order approximation had a tendency to be rather more explosive on the tails, to be misbehaved in the various ways that I indicated in my early lecture on the tails than the first order approximation. It would very often prove to be the case that the A2 and the B2 were rather good at approximating it throughout, say, the middle 50% of the distribution, but that they went astray rather when you got onto the tails of the distribution. Since we were looking particularly at the tails, that really had the effect of making the A2 and the B2 look rather poor by comparison. Well, so that's really all I think I have time to say about our work in this field. Okay. Not really, no. I'm going to talk more about what you shouldn't do than what you should do. And what I've got, which I'm going to report finally, are some results on pre-testing, where